Okay, this is 2019, problem set 2, problem number 2. The toy rocket of mass half a kilogram starts from rest on the ground, launched upward, experience a vertical net force. So that's the one that we're going to look at first. So the first thing that I see is the rocket's upward acceleration is given by this equation, and then they give me some values for K and L. So I'm going to put those in this equation. So I'm going to start with the acceleration is equal to 9 minus 0.25 t squared. And so there's my acceleration equation. All right, just so that I kind of see what's going, well, I'll wait and I'll say that in a second. At 6 seconds, so this is for 6 seconds, and at 6 seconds, okay, then my acceleration is going to be negative 9.8 meters per second squared, because then gravity is going to take over and we're going to accelerate toward the ground like that. So on A, it says calculate the magnitude of the net impulse exerted on the rocket from 0 to 6. Now, if you look at the equation sheet, you will see this. And so absolutely that is a legitimate way to do it, is to integrate the force equation, which you can get force by doing mass times acceleration. And remember, our mass is a half a kilogram. So we could do mass times acceleration and integrate that function, and that would be fine. But with my students, a lot of times we talk about impulse being change in momentum, and change in momentum is mass times change in velocity. And I think maybe this might be an easier approach to think of or to remember. So I go and I say, well, if I think about my calculus side of things, I've got acceleration. So how could I get velocity? Well, acceleration is the derivative of velocity. So dv dt is equal to 9 minus 0.25 t squared. So dv is going to equal 9 minus 0.25 t squared dt, and then I'm going to integrate both sides. So I get my change in velocity by integrating this function from 0 to 6. And go ahead and take the integral of that, which, I mean, what are we doing? We would have integrated force. We're integrating acceleration. So we're really doing the same thing, but again, this is how my kids probably would think of it better. So I'm going to integrate this function, so I get 9t minus 2.25 t cubed over 3, evaluated from 0 to 6. And so I don't have to do the evaluation at 0 because I'm going to plug that in. I'll go ahead and write this. So I get 9 times 6 minus 0.25 times 6 cubed over 3 minus essentially 0. Because if I plug 0 in here, I get 0 and 0. And so we can evaluate that. All right, and I get 36 meters per second. So that's my delta V. So that's what I'm going to go back and I'm going to plug in here. So my mass is a half a kilogram times that 36 meters per second, and I get 18 kilogram meters per second, which is the same thing as 18 newtons times seconds, which usually when we do impulse, we record it in those units. So there's my impulse or change of momentum for that time period. Now on B, they asked me to calculate the speed of the rocket, and this is kind of why I like the approach that we just did, the velocity at 6 seconds. Well, I just did change in velocity, which was the velocity at 6 minus the velocity at 0, and the velocity at 0 was 0, so the velocity at 6 must be 36. CA. So I can go back and say, hey, I did that just a second ago. Right. Right, then I go to C, and it says calculate the kinetic energy of the rocket at 6. Well, and that's on I, excuse me. Kinetic energy is 1/2 mv squared. So I'm going to do 1/2 times my mass of half a kilogram times my velocity squared. And so that's going to give me 324, and remember energy is in joules as long as we're in kilograms and meters per second here. I didn't write my meters per second in there, but that's, again, it's okay as long as you've got the correct units on everything to start with, you get the correct in the end. All right, then we go to D, or excuse me, not D yet. We're going to go to II. It says calculate the change in gravitational potential energy from 0 to 6. Well, I look at that and I go, okay, delta U. So that's going to be U final minus U naught. So that's mgh final minus mgh naught. I know M, I know G, I don't know H. Okay, I do know H naught though. H naught is 0. Okay, I can do that because I start at the ground. So I know this term falls away. So the change in potential energy is just going to be what my potential energy is at that point. So I need to know how high did my rocket go. Well, I'm not traveling at a constant velocity. My acceleration is not constant, so this is not a kinematic problem, but I can go, hey, you know what? I did acceleration and to velocity by integrating. So I'm going to do the same thing. I'm going to say, well, dx dt, or in this case, dy dt, you can do it either way, is going to equal this velocity equation, which is 9t minus 0.25 t cubed over 3. So I'm going to integrate this. I'm going to do the integral of dx, and remember I'm going to multiply dt by both sides. So I'm going to integrate 9t minus 0.25 t cubed over 3, and I'm going from 0 to 6. So that's going to give me my delta x, because this is going to give me, this is from x initial to x final. So that's where I'm going. All right, now I'm going to integrate this. So I'm going to get 9t squared over 2 minus 0.25 t to the 4th over. Now there would be a 4 down here, but there's already a 3, so 4 times 3 is 12. And I'm going to evaluate that from 0 to 6. So we plug that in, I get 9 times 6 squared over 2 minus 0.25 times 6 to the 4th over 12. Now there's my 6 part, but if I plug in 0, what do I get? I get 0, because 9 times 0 squared, 0.25 times 0 to the 4th. So the 0 doesn't have any effect on this. And essentially this would give me my delta H, so I could factor this out and say mg H final minus H naught, and that would be what this is, but again, that's 0, so do that, minus 0.25 times 6 to the 4th divided by 12, and it says that I get 135 meters. So I'm going to take that back here and put in a half a kilogram times 9.8 meters per second squared times 135 meters to get my change in potential energy of 661.5, so 660 joules. Okay. All right. Now, D. Part D says, calculate the maximum height reached by the rocket relative to its launching point. Okay, so I know, here's my rocket's path. I know I travel 135 meters while accelerating at the 9 minus 0.25 t squared acceleration that I have. Okay, but then I travel some more while my acceleration is negative 9.8 meters per second squared. Okay, but I don't know what that is. And so if I want to find my max height, I need to find this and add it to 135. So how could I find this? Well, I know on this little path my 6 seconds. I know my acceleration is this. I'm looking for, I realize this is delta y, but I'm going to call it delta x, because it really doesn't matter as long as you're, staying in one dimension. And I know that when I get to the top, my rocket is going to stop, because everything that goes up, 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 it eventually stops and then it comes back down. So I've got these pieces. I've got V final, V naught, delta x, and A. And now I am under a constant acceleration, so kinematics can work. So I say, well, V final squared is V naught squared plus 2A delta x. V final is 0, V naught is 36, the acceleration is negative 9.8, and I'm looking for how high did I go. So I subtract 36 squared from both sides. Go ahead and multiply that out, divide by negative 19.6. So 36 squared divided by 19.6 is 66 meters. So that's what I'm going to add to this. So my total height is going to be 135 meters plus that 66 meters for a total of 201 meters. So that is how high my rocket's going to go at max height. Okay. Last thing is they give us a little graph here, and they say, okay, so you've got a graph of velocity versus time, and they say here's t-top. So that's when I reach the top, and they want me to graph what's going on in this whole thing. Okay, well, at some point in time, I get up here to 36. Okay, you don't really have to draw this in, but let's say some point in time I reach that 36 meters per second. Okay, I know when I get to the peak of my flight, I'm gonna be going 0. And I know my acceleration from here on out is negative 9.8. So the slope of that is going to be negative 9.8 meters per second squared. So I just need to know, what am I doing in the beginning? So if I look at that acceleration equation, which was 9 minus 0.25 t squared. Okay, at 0, my acceleration is 9. So it is big and positive. Okay, maybe not quite that big, kind of like this. But as I start getting a bigger time over here, this starts decreasing. As this starts decreasing, this whole value starts decreasing. And where do I approach? Well, I approach 0. Because when I get to that final point where I get to the point where basically I'm not getting any more thrust from the rocket, so I'm getting to that point. So that's what I should have coming up.